The Lockheed Sr-71 Blackbird was an advanced, long-range, Mach 3+ strategic reconnaissance aircraft. It was developed as a black project from the Lockheed A-12 reconnaissance aircraft in the 1960s by Lockheed and its Skunk Works division. Clarence Kelly Johnson was responsible for many of the design's innovative concepts. During reconnaissance missions, the SR-71 operated at high speeds and altitudes to allow it to outrace threats. If a surface-to-air missile launch was detected, the standard evasive action was simply to accelerate and outfly the missile. The SR-71 served with the U.S. Air Force from 1964 to 1998. A total of 32 aircraft were built. 12 were lost in accidents, but none lost to enemy action. The SR-71 has been given several nicknames, including Blackbird and Habu. Since 1976, it has held the world record for the fastest air-breathing manned aircraft, a record previously held by the YF-12. Development. Background. Lockheed's previous reconnaissance aircraft was the relatively slow U-2, designed for the Central Intelligence Agency. The 1960 downing of Francis Gary Powers' U-2 underscored the aircraft's vulnerability and the need for faster reconnaissance aircraft. The CIA turned again to Kelly Johnson and Lockheed's Skunk Works, who developed the A-12 and would go on to build upon its design concepts for the SR-71. The flight test engineer in charge was Joseph F. Ware, Jr. The A-12 first flew at Groom Lake, Nevada, on April 25, 1962. 13 were built. 2 variants were also developed, including 3 YF-12A interceptor prototypes, and 2 M21 drone carrier variants. The aircraft was meant to be powered by the Pratt & Whitney J58 engine, but development ran over schedule, and it was equipped instead with a less powerful Pratt & Whitney J75. The J58s were retrofitted as they became available, and became the standard power plant for all subsequent aircraft in the series as well as the SR-71. The A-12 flew missions over Vietnam and North Korea before its retirement in 1968. The program's cancellation was announced on December 28, 1966, due both to budget concerns and because of the forthcoming SR-71. SR-71. The SR-71 designator is a continuation of the pre-1962 bomber series. The last aircraft built using the series was the XB-70 Valkyrie. However, a bomber variant of the Blackbird was briefly given the B-71 designator, which was retained when the type was changed to SR-71. During the later period of its testing, the B-70 was proposed for a reconnaissance strike role, with an RS-70 designation. When it was clear that the A-12 performance potential was much greater, the Air Force ordered a variant of the A-12 in December 1962. Originally named A-12 by Lockheed, the Air Force version was longer and heavier than the A-12, with a longer fuselage to hold more fuel, 2 seats in the cockpit, and reshaped chines. Reconnaissance equipment included signals intelligence sensors, a side-looking radar and a photo camera. The CIA's A-12 was a better photo reconnaissance platform than the Air Force's A-12, since the A-12 flew somewhat higher and faster, and with only one pilot it had room to carry a superior camera and more instruments. During the 1964 campaign, Republican presidential nominee Barry Goldwater repeatedly criticized President Lyndon B. Johnson and his administration for falling behind the Soviet Union in developing new weapons. Johnson decided to counter this criticism by revealing the existence of the YF-12A Air Force Interceptor, which also served as cover for the still-secret A-12, and the Air Force reconnaissance model since July 1964. Air Force Chief of Staff General Curtis LeMay preferred the SR designation and wanted the RS-71 to be named SR-71. Before the July speech, LeMay lobbied to modify Johnson's speech to read SR-71 instead of RS-71. The media transcript given to the press at the time still had the earlier RS-71 designation in places, creating the story that the president had misread the aircraft's designation. In 1968, Secretary of Defense Robert McNamara canceled the F-12 interceptor program. The specialized tooling used to manufacture both the YF-12 and the SR-71 was also ordered destroyed. Production of the SR-71 totaled 32 aircraft with 29 Steradians-71S, 2 Steradians-71BS, and the single SR-71C. Design. The SR-71 was designed for flight at over Mach 3 with a flight crew of 2 in tandem cockpits, with the pilot in the forward cockpit and the reconnaissance systems officer monitoring the surveillance systems and equipment from the rear cockpit. The SR-71 was designed to minimize its radar cross-section, an early attempt at stealth design. Finished aircraft were painted a dark blue, almost black, to increase the emission of internal heat and to act as camouflage against the night sky. The dark color led to the aircraft's call sign Blackbird. Airframe. On most aircraft, use of titanium was limited by the costs involved in procurement and manufacture. It was generally used only in components exposed to the highest temperatures, such as exhaust fairings and the leading edges of wings. On the SR-71, titanium was used for 85% of the structure, with much of the rest polymer composite materials. To control costs, Lockheed used a more easily worked alloy of titanium which softened at a lower temperature. The challenges posed by the SR-71 led Lockheed to develop entirely new fabrication methods to enable its manufacture, and have since been used in the manufacture of many other aircraft. Welding the titanium requires distilled water, as the chlorine present in tap water is corrosive. Commonplace cadmium-plated tools could not be used as they also caused corrosion. Metallurgical contamination was another problem. At one point 80% of the delivered titanium for manufacture was rejected on these grounds. The high temperatures generated during flight required special design and operating techniques. For example, major portions of the skin of the inboard wings were corrugated, not smooth. The heat of flight would have caused a smooth skin to split or curl, but the corrugated skin could expand vertically and horizontally. The corrugation also increased longitudinal strength. Similarly, the fuselage panels were manufactured to fit only loosely on the ground. Proper alignment was achieved only when the airframe heated up and expanded several inches. Because of this, and the lack of a fuel sealing system that could handle the thermal expansion of the airframe at extreme temperatures, the aircraft would leak JP-7 jet fuel on the runway. At the beginning of each mission, the aircraft would make a short sprint after takeoff to warm up the airframe, then refuel before heading off to its destination. Cooling was carried out by cycling fuel behind the titanium surfaces in the chines. On landing, the canopy temperature was over 300 degrees Celsius. The red stripes on some SR-71s were to prevent maintenance workers from damaging the skin. Near the center of the fuselage, the curved skin was thin and delicate, with no support from the structural ribs, which were spaced several feet apart. Stealth and threat avoidance. The first operational aircraft designed around a stealthy shape and materials, the SR-71 had several features designed to reduce its radar signature. The SR-71 had a radar cross-section of around 10 square meters. Drawing on the first studies in radar stealth technology, which indicated that a shape with flattened, tapering sides would reflect most radar energy away from the radar beam's place of origin, engineers added chines and canted the vertical control surfaces inward. Special radar-absorbing materials were incorporated into sawtooth-shaped sections of the aircraft's skin. Cesium-based substances were added to the fuel to somewhat reduce the visibility of the exhaust plumes to radar, although the large and hot exhaust stream produced at speed remained quite apparent. For all this effort, Kelly-Johnson later conceded that Soviet radar technology advanced faster than the stealth technology employed against it. The SR-71 carried electronic countermeasures, but its greatest protection was its high speed and cruising altitude that made it almost invulnerable to the weapons of its day. Merely accelerating would typically be enough to evade a surface-to-air missile, and the plane was faster than the Soviet Union's principal interceptor, the MiG-25. During its service life, no SR-71 was shot down. Chines. The SR-71 featured chines, a pair of sharp edges leading aft from either side of the nose along the fuselage. These were not a feature on the early A-3 design. Dr. Frank Rogers of the Scientific Engineering Institute, a CIA front organization, had discovered that a cross-section of a sphere had a greatly reduced radar reflection, and adapted a cylindrical-shaped fuselage by stretching out the sides of the fuselage. After the advisory panel provisionally selected Convair's fish design over the A3 on the basis of RCS, Lockheed adopted chines for its A4 through A6 designs. Aerodynamicists discovered that the chines generated powerful vortices and created additional lift, leading to unexpected aerodynamic performance improvements. The angle of incidence of the delta wings could then be reduced for greater stability and less drag at high speeds. More weight, such as fuel, could be carried to increase range. Landing speeds were also reduced, since the chines vortices created turbulent flow over the wings at high angles of attack, making it harder for the wings to stall. High alpha turns were limited by the capability of the engine inlets to ingest air, possibly resulting in flameout. Pilots were thus warned not to pull more than 3G in to avoid high angles of attack. The chines also acted like the leading-edge extensions that increased the agility of modern fighters such as the F-5, F-16, FA-18, MiG-29 and Su-27. The addition of chines also enabled the removal of the planned canard foreplanes. Air inlets. The air inlets allowed the SR-71 to cruise at over Mach 3.2 while keeping airflow into the engines at the initial subsonic speeds. Mach 3.2 was the design point for the aircraft, its most efficient speed. At the front of each inlet, a pointed, movable cone called a spike was locked in its full forward position on the ground and during subsonic flight. When the aircraft accelerated past Mach 1.6, an internal jack screw moved the spike up to 26 inches inwards, directed by an analog air inlet computer that took into account pitot's static, pitch, roll, yaw, and angle of attack. Moving the spike tip drew the shock wave riding on it closer to the inlet cowling until it touched just slightly inside the cowling lip. This position reflected the spike shock wave repeatedly between the spike's center body and the inlet inner cowl sides, and minimized airflow spillage, which is the cause of spillage drag. The air slowed supersonically with a final plane shock wave at entry to the subsonic diffuser. Downstream of this normal shock wave the air is subsonic. It decelerates further in the divergent duct to give the required speed at entry to the compressor. Capture of the plane shock wave within the inlet is called starting the inlet. Bleed tubes and bypass doors were designed into the inlet and engine nacelles to handle some of this pressure and to position the final shock to allow the inlet to remain started. The SR-71 was sometimes more efficient at speeds higher than Mach 3.2 in terms of pounds of fuel burned per nautical mile traveled. This depended on the outside air temperature. During one mission, SR-71 pilot Brian Schull flew faster than usual for some time to avoid multiple interception attempts. Afterwards, it was discovered that this had reduced fuel consumption. In the early years of operation, the analog computers would not always keep up with rapidly changing flight environmental inputs. If internal pressures became too great and the spike was incorrectly positioned, the shock wave would suddenly blow out the front of the inlet, called an inlet unstart. During unstarts afterburner extinctions were common. The remaining engine's asymmetrical thrust would cause the aircraft to yaw violently to one side. SAS, autopilot, and manual control inputs would fight the yawing, but often the extreme off angle would reduce airflow in the opposite engine and stimulate sympathetic stalls. This generated a rapid counter-yawing, often coupled with loud banging noises, and a rough ride during which crews' helmets would sometimes strike their cockpit canopies. One response to a single unstart was unstarting both inlets to prevent yawing, then restarting them both. Lockheed later installed an electronic control to detect unstart conditions and perform this reset action without pilot intervention. Beginning in 1980, the analog inlet control system was replaced by a digital system, which reduced unstart instances. Engines. The SR-71's Pratt & Whitney JT11D20 engine was a considerable innovation of the era. The engine could produce a static thrust of 32,500 pound-forces. The engine was most efficient around Mach 3.2, the Blackbird's typical cruising speed. At lower speeds, the turbojet provided most of the compression. At higher speeds, the engine largely ceased to provide the thrust which now came from fuel burned in the afterburner. Air was initially compressed by the inlet spike and subsequent converging duct between the center body and inlet cowl. The shock waves generated slowed the air to subsonic speeds relative to the engine. The air then entered the engine compressor. Some of this compressor flow was removed after the fourth compressor stage and went straight to the afterburner through 6 bypass tubes. The air passing through the turbojet was compressed further by the remaining 5 compressor stages and then fuel was added to it in the combustion chamber. After passing through the turbine, the exhaust, together with the compressor bleed air, entered the afterburner. At around Mach 3, the temperature rise from the intake compression, added to the engine compressor temperature rise, reduced the allowable fuel flow because the turbine temperature limit did not change. The rotating machinery produced less power but still enough to run at 100% RPM, thus keeping the airflow through the intake constant. The rotating machinery had become a drag item and the engine thrust at high speeds came from the afterburner temperature rise. The maximum flight speed was limited by the temperature of the air entering the engine compressor at 800 degree Fahrenheit. The engines were not certified beyond that temperature. The Blackbird's engines were originally started with the assistance of an external engine referred to as a start cart. The cart included 2 Buick Wildcat V8 engines positioned underneath the aircraft. The 2 engines powered a single, vertical drive shaft connecting to a single J58 engine. Once one jet engine was started, the cart was wheeled to the other side of the aircraft to start the other engine. The operation was deafening. Later, big block Chevrolet engines were used. Eventually, a quieter, pneumatic start system was developed for use at Blackbird main operating bases, but the start carts remained to support recovery team Blackbird starts at diversion landing sites not equipped to start J58 engines. Fuel: several exotic fuels were investigated for the Blackbird. Development began on a coal slurry power plant, but Johnson determined that the coal particles damaged important engine components. Research was conducted on a liquid hydrogen power plant, but the tanks for storing cryogenic hydrogen were not of a suitable size or shape. In practice, the Blackbird would burn somewhat conventional JP7 which was difficult to light. To start the engines, triethylbron, which ignites on contact with air, was injected to produce temperatures high enough to ignite the JP7. The TEB produced a characteristic green flame, which could often be seen during engine ignition. Aerial refueling: the SR-71 required in-flight refueling to replenish the fuel expended on takeoff and during long-duration missions. Its supersonic mission segments generally lasted no more than 90 minutes before the pilot had to find a tanker. To accomplish this, specialized KC-135Q tankers were required to refuel the SR-71. The Q model tanker had a modified high-speed boom, which would allow refueling of the Blackbird at nearly the tanker's maximum airspeed, with minimum flutter. The Q model also had a separate fuel system, which kept the tanker's fuel isolated from the JP7 needed by the SR-71. During its operational life, the SR-71 had dedicated KC-135QS and air crews on alert, ready to launch within minutes to refuel a Blackbird. Some of these aircraft were located on the East Coast. On the West Coast, at Hickam AFB, Hawaii, RAF Mildenhall, England, and Guam. Some of the original KC-135Q aircraft are still serving on active duty in the U.S. Air Force inventory as the KC-135T, a new designation given after the aircraft have been upgraded re-engined to the KC-135 as standard by installation of more powerful and fuel-efficient CFM56 engines and upgraded avionics. They can be identified by the 2 single-point refueling panels located in the left and right wheel wells, instead of only a single panel in the left wheel well. The KC-135QT aircraft also had several hundred pounds of ballast in the nose compartment to maintain weight and balance. As an aid to the pilot when refueling, the cockpit was fitted with a peripheral vision horizon display. This unusual instrument displayed a barely visible artificial horizon, which gave the pilot subliminal cues on aircraft attitude. Astro-inertial navigation system. The USAF sought a precision navigation system for maintaining route accuracy and target tracking at very high speeds, superior to the inertial navigation systems used by the preceding U-2 and A-12. Nortronics, Northrop's Electronics Development Division, had developed an astro-inertial navigation system, which could correct navigation errors with celestial observations, for the SM-62 Snark missile, and a separate system for the ill-fated AGM-48 Skibald missile, the latter of which was adapted for the SR-71. Before each takeoff, a primary alignment brought the ANS's inertial components to a high degree of accuracy. Once in flight, the ANS, which sat behind the reconnaissance systems officer's position, tracked stars through a circular window of quartz glass set in the upper fuselage. Its blue light source star tracker, which could see stars during both day and night, would continuously track a variety of stars as the aircraft's changing position brought them into view. The system's digital computer ephemeris contained data on 56 stars. The ANS could supply altitude and position to flight controls and other systems, including the mission data recorder, auto-nav steering to preset destination points, automatic pointing and control of cameras and sensors, and optical or SLR sighting of fixed points loaded into the ANS before takeoff. Former pilot Richard Graham told an interviewer at the Frontiers of Flight Museum that the navigation system was good enough to limit drift to 1,000 feet off the direction of travel at Mach 3. The original B-1A offensive avionics request for proposal required the installation and integration of an NAS-14 system, but cost-cutting changes later deleted it from the B-1. Some U-2RS did receive the NAS-21 system, but newer inertial and GPS systems replaced them. Sensors and payloads. The SR-71 originally included optical infrared imagery systems, side-looking airborne radar, electronic intelligence gathering systems, defensive systems for countering missile and airborne fighters, and recorders for SLAR, ELINT and maintenance data. The SR-71 carried a Fairchild tracking camera and an HRB Singer infrared camera, both of which ran during the entire mission for route documentation, to respond to any accusations of overflight. Because the SR-71 carried an observer behind the pilot, it could not use the A-12's principal sensor, a single large focal-length optical camera that sat in the cube bay behind the cockpit. Instead, camera systems could be located either in the wing chines or the aircraft's interchangeable nose. Wide-area imaging was provided by two of ATEC's operational objective cameras, which provided stereo imagery across the width of the flight track, or an ATEC optical bar camera, which gave continuous horizon-to-horizon coverage. A closer view of the target area was given by the HYCON technical objective camera, that could be directed up to 45 degrees left or right of the centerline. Initially, the TEOCs could not match the resolution of the A-12's larger camera, but rapid improvements in both the camera and film improved this performance. Side-looking radar, built by Goodyear Aerospace, could be carried in the removable nose. In later life, the radar was replaced by L'Oreal's advanced synthetic aperture radar system. Both the first SLR and ASARS-1 were ground mapping imaging systems, collecting data either in fixed swaths left or right of centerline or from a spot location for higher resolution. ELINT gathering systems, called the Electromagnetic Reconnaissance System, built by AL, could be carried in the chine bays to analyze electronic signal fields being passed through, and were pre-programmed to identify items of interest. Over its operational life, the Blackbird carried various electronic countermeasures, including warning and active electronic systems built by several ECM companies and called systems A, A2, A2C, B, C, C2, E, G, H and M. On a given mission, an aircraft would carry several of these frequency-purpose payloads to meet the expected threats. After landing, recording systems and gathered information from the SLR and ELINT systems, and the maintenance data recorder were subjected to post-flight ground analysis. In the later years of its operational life, A data link system could send ASARS-1 and ELINT data from about 2,000 mi of track coverage to a suitably equipped ground station. Life support. Flying at 80,000 aft meant that crews could not use standard masks, which could not provide enough oxygen above 43,000 aft. Specialized protective pressurized suits were produced by the David Clark Company for the A-12, YF-12, M-21 and SR-71. Furthermore, an emergency ejection at Mach 3.2 would subject crews to an instant heat rise of about 450 degree Fahrenheit. Thus, during a high-altitude ejection scenario, an onboard oxygen supply would keep the suit pressurized during the descent. The cockpit could be pressurized to an altitude of 10,000 or 26,000 ft during flight. The cabin needed a heavy-duty cooling system, for cruising at Mach 3.2 would heat the aircraft's external surface well beyond 500 degree Fahrenheit and the inside of the windshield to 250 degree Fahrenheit. An air conditioner used a heat exchanger to dump heat from the cockpit into the fuel prior to combustion. Operational history. The first flight of an Blackbird-71 took place on December 22, 1964, at Air Force Plant 42 in Palmdale, California. The SR-71 reportedly reached a top speed of Mach 3.4 during flight testing. The first SR-71 to enter service was delivered to the 4200th Strategic Reconnaissance Wing at Beale Air Force Base, California, in January 1966. SR-71s first arrived at the 9th SRW's operating location at Kadena Air Base, Okinawa on March 8, 1968. These deployments were codenamed Glowing Heat, while the program as a whole was codenamed Senior Crown. Reconnaissance missions over North Vietnam were codenamed Giant Scale. On March 21, 1968, Major Jerome F. O'Malley and Major Edward D. Payne flew the first operational SR-71 sortie in SR-71 serial number 61 to 7976 from Kadena AB, Okinawa. During its career, this aircraft accumulated 2,981 flying hours and flew 942 total sorties, including 257 operational missions, from Beale AFB, Palmdale, California, Kadena Air Base, Okinawa, Japan, and RAF Mildenhall, UK. The aircraft was flown to the National Museum of the United States Air Force near Dayton, Ohio in March 1990. From the beginning of the Blackbird's reconnaissance missions over enemy territory in 1968, the SR-71s averaged approximately one sortie a week for nearly 2 years. By 1970, the SR-71s were averaging 2 sorties per week, and by 1972, they were flying nearly 1 sortie every day. 2 SR-71s were lost during these missions, one in 1970 and the second aircraft in 1972, both due to mechanical malfunctions. While deployed in Okinawa, the SR-71s and their aircrew members gained the nickname Habu after a pit viper indigenous to Japan, which the Okinawans thought the plane resembled. Swedish Air Force fighter pilots, using the predictable patterns of SR-71 routine flights over the Baltic Sea, managed to lock their radar on the SR-71 on numerous occasions. Despite heavy jamming from the SR-71, target illumination was maintained by feeding target location from ground-based radars to the fire control computer in the January 37 Viggen interceptor. The most common site for the lock-on to occur was the thin stretch of international airspace between Åland and Gotland that the SR-71 used on the return flight. Operational highlights for the entire Blackbird family as of about 1990 included 3,551 mission sorties flown, 17,300 total sorties flown, 11,008 mission flight hours, 53,490 total flight hours, 2,752 hours Mach 3 time, 11,675 hours Mach 3 time. Only one crew member, Jim Swear, a Lockheed Flight Test Reconnaissance and Navigation Systems specialist, was killed in a flight accident. The rest of the crew members ejected safely or evacuated their aircraft on the ground. Initial retirement. In the 1970s, the SR-71 was placed under closer congressional scrutiny and, with budget concerns, the program was soon under attack. Both Congress and the USAF sought to focus on newer projects like the B-1 Lancer and upgrades to the B-52 Stratofortress, whose replacement was being developed. The SR-71 had never gathered significant supporters within the Air Force, making it an easy target for cost-conscious politicians. Dick Cheney told the Senate Appropriations Committee that the SR-71 cost $85,000 per hour to operate. Opponents of the program estimated it cost $400 million per year to support. That number was subsequently reduced to $260 million. Also, parts were no longer being manufactured for the aircraft, so other airframes had to be cannibalized to keep the fleet airworthy. The aircraft's lack of a data link meant that imagery and radar data could not be used in real time, but had to wait until the aircraft returned to base. The Air Force saw the SR-71 as a bargaining chip which could be sacrificed to ensure the survival of other priorities. A general misunderstanding of the nature of aerial reconnaissance and a lack of knowledge about the SR-71 in particular was used by detractors to discredit the aircraft, with the assurance given that a replacement was under development. In 1988, Congress was convinced to allocate $160,000 to keep 6 SR-71s in flyable storage that would allow the fleet to become airborne within 60 days. The USAF refused to spend the money. While the SR-71 survived attempts to retire it in 1988, partly due to the unmatched ability to provide high-quality coverage of the Kola Peninsula for the U.S. Navy, the decision to retire the SR-71 from active duty came in 1989. With the SR-71 flying its last missions in October that year. Funds were redirected to the financially troubled B-1 Lancer and B-2 Spirit programs. 4 months after the plane's retirement, General Norman Schwarzkopf, Jr., was told that the expedited reconnaissance which the SR-71 could have provided was unavailable during Operation Desert Storm. Reactivation, due to increasing unease about political conditions in the Middle East and North Korea. The U.S. Congress re-examined the SR-71 beginning in 1993. At a hearing of the Senate Committee on Armed Services, Senator J. James Exon asked Admiral Richard C. Mach, "If we have the satellite intelligence that you collectively would like us to have, would that type of system eliminate the need for an SR-71? Or even if we had this blanket up there that you would like in satellites, do we still need an SR-71?" Mach replied, "From the operator's perspective, what I need is something that will not give me just a spot in time but will give me a track of what is happening. When we are trying to find out if the Serbs are taking arms, moving tanks or artillery into Bosnia, we can get a picture of them stacked up on the Serbian side of the bridge. We do not know whether they then went on to move across the bridge. We need the data that a tactical, and SR-71, a U-2, or an unmanned vehicle of some sort, will give us, in addition to, not in replacement of, the ability of the satellites to go around and check not only that spot but a lot of other spots around the world for us. It is the integration of strategic and tactical." Rear Admiral Thomas F. Hall addressed the question of why the SR-71 was retired, saying it was under the belief that, given the time delay associated with mounting a mission, conducting a reconnaissance, retrieving the data, processing it, and getting it out to a field commander, that you had a problem in timelines that was not going to meet the tactical requirements on the modern battlefield. And the determination was that if one could take advantage of technology and develop a system that could get that data back real time, that would be able to meet the unique requirements of the tactical commander. Hall stated that the Advanced Airborne Reconnaissance System, which was going to be an unmanned UAV, would meet the requirements but was not affordable at the time. He said that they were looking at alternative means of doing the job of the SR-71. Mach told the committee that they were flying U-2s, RC-135s, and other strategic and tactical assets to collect information in some areas. Senator Robert Byrd and other senators complained that the better-than-successor to the SR-71 had yet to be developed at the cost of a good enough serviceable aircraft. They maintained that, in a time of constrained military budgets, designing, building, and testing an aircraft with the same capabilities as the SR-71 would be impossible. Congress' disappointment with the lack of a suitable replacement for the Blackbird was cited concerning whether to continue funding imaging sensors on the U-2. Congressional conferees stated the experience with the SR-71 serves as a reminder of the pitfalls of failing to keep existing systems up to date and capable in the hope of acquiring other capabilities. It was agreed to add $100 million to the budget to return 3 SR-71s to service, but it was emphasized that this would not prejudice support for long-endurance UAVs, such as the Global Hawk. The funding was later cut to $72.5 million. The Skunk Works was able to return the aircraft to service under budget at $72 million. Colonel J. Murphy was made the program manager for Lockheed's reactivation plans. Retired Air Force Colonels Don Emmons and Barry McKean were put under government contract to remake the plane's logistic and support structure. Still active Air Force pilots and reconnaissance systems officers who had worked with the aircraft were asked to volunteer to fly the reactivated planes. The aircraft was under the command and control of the 9th Reconnaissance Wing at Beale Air Force Base and flew out of a renovated hangar at Edwards Air Force Base. Modifications were made to provide a data link with near real-time transmission of the advanced synthetic aperture radar's imagery to sites on the ground. Final retirement. The reactivation met much resistance. The Air Force had not budgeted for the aircraft, and UAV developers worried that their programs would suffer if money was shifted to support the SR-71s. Also, with the allocation requiring yearly reaffirmation by Congress, long-term planning for the SR-71 was difficult. In 1996, the Air Force claimed that specific funding had not been authorized, and moved to ground the program. Congress reauthorized the funds, but, in October 1997, President Bill Clinton attempted to use the line-item veto to cancel the $39 million allocated for the SR-71. In June 1998, the Supreme Court of the United States ruled that the line-item veto was unconstitutional. All this left the SR-71's status uncertain until September 1998, when the Air Force called for the funds to be redistributed. The plane was permanently retired in 1998. The Air Force quickly disposed of its SR-71s, leaving NASA with the 2 last airworthy Blackbirds until 1999. All other Blackbirds have been moved to museums except for the 2 SR-71s and a few D-21 drones retained by the NASA Dryden Flight Research Center. SR-71 timeline, important dates pulled from many sources. December 24, 1957, first J-58 engine run. May 1, 1960, Francis Gary Powers is shot down in a Lockheed U-2 over the Soviet Union. June 13, 1962, SR-71 mock-up reviewed by Air Force. July 30, 1962, J-58 completes pre-flight testing. December 28, 1962, Lockheed signs contract to build 6 SR-71 aircraft. July 25, 1964, President Johnson makes public announcement of SR-71. October 29, 1964, SR-71 prototype delivered to Air Force Plant 42 at Palmdale, California. December 7, 1964, BAFB, CA, announced as base for SR-71. December 22, 1964, first flight of the SR-71 with Lockheed test pilot Bob Gilliland at Air Force Plant No. 42. July 21, 1967, Jim Watkins and Dave Dempster fly first international sortie in SR-71A, AFSAIR. No. 61 to 7972, when the Astro-Inertial Navigation System fails on a training mission and they accidentally fly into Mexican airspace. November 3, 1967, A-12 and SR-71 conduct a reconnaissance fly-off. Results are questionable. February 5, 1968, Lockheed ordered to destroy A-12, YF-12, and SR-71 tooling. March 8, 1968, first SR-71A arrives at Kadena AB, Okinawa to replace A-12s. March 21, 1968, first SR-71 operational mission flown from Kadena AB over Vietnam. May 29, 1968, CMS-GT Bill Gornick begins the tie-cutting tradition of Habu cruise neckties. December 3, 1975, first flight of SR-71A in big-tail configuration. April 20, 1976, TDY operations started at RAF Mildenhall, United Kingdom with SR-71A, AFSAIR. Number 61 to 7972. 27 July 28, 1976, SR-71A set speed and altitude records and speed over a straight course, 2,193.167 miles per hour. August 1980, Honeywell starts conversion of AFICS to DVIX. January 15, 1982, SR-71B, AFSAIR. Number 61 to 7956, flies its 1000th sortie. April 21, 1989, SR-71, AFSAIR. Number 61 to 7974, is lost due to an engine explosion after taking off from Kadena AB. This is the last Blackbird to be lost, and is the first SR-71 accident in 17 years. November 22, 1989, Air Force Senior 71 program officially terminated. January 21, 1990, last SR-71, AFSAIR. Number 61 to 7962, leaves Kadena AB. January 26, 1990, SR-71 is decommissioned at Beale AFB, CAR. March 6, 1990, last SR-71 flight under Senior Crown Program, setting 4 speed records en route to Smithsonian Institution. July 25, 1991, SR-71B, AFSAIR. Number 61 to 7956/NASA number 831 officially delivered to NASA Dryden Flight Research Center at Edwards AFB, California. October 1991, NASA engineer Marta Bon Mayer becomes the first female SR-71 crew member. September 28, 1994, Congress votes to allocate $100 million for reactivation of 3 SR-71s. April 26, 1995, first reactivated SR-71A makes its first flight after restoration by Lockheed. June 28, 1995, first reactivated SR-71 returns to Air Force's Detachment 2. August 28, 1995, second reactivated SR-71A makes first flight after restoration. August 2, 1997, a NASA Senior 71 makes multiple flybys at the EAA AirVenture Oshkosh Air Show. It is then supposed to perform a sonic boom at 53,000 feet after a mid-air refueling, but a fuel flow problem causes it to divert to Milwaukee. 2 weeks later, the pilot's flight path brings him over Oshkosh again, and there is, in fact, a sonic boom. October 19, 1997, the last flight of SR-71B, AFSAIR. Number 61 to 7956 at Edwards AFB Open House. October 9, 1999, the last flight of the SR-71 September 2002, final resting places of aircraft number 956, number 971, and number 980 are made known. December 15, 2003, SR-71, AFSAIR. Number 61 to 7972, goes on display at the Smithsonian National Air and Space Museum's Stephen F. Vorhazy Center at Washington Dulles International Airport in Chantilly, Virginia. Records. The SR-71 was the world's fastest and highest-flying operational manned aircraft throughout its career. On July 28, 1976, SR-71 serial number 61 to 7962. Broke the world record, an absolute altitude record of 85,069 feet. Several aircraft have exceeded this altitude in zoom climbs, but not in sustained flight. That same day SR-71, serial number 61 to 7958, set an absolute speed record of 1,905.81 knots, approximately Mach 3.3. The SR-71 also holds the speed over a recognized course record for flying from New York to London, the Euro distance 3,508 miles. 1,435.587 miles per hour, and an elapsed time of 1 hour 54 minutes and 56.4 seconds. Set on September 1, 1974 while flown by U.S. Air Force pilot Major James V. Sullivan and Major Noel F. Whitfield, Reconnaissance Systems Officer. This equates to an average velocity of about Mach 2.68, including deceleration for in-flight refueling. Peak speeds during this flight were likely closer to the declassified top speed of Mach 3.2+. For comparison, the best commercial Concorde flight time was 2 hours 52 minutes and the Boeing 747 average is 6 hours 15 minutes. On April 26, 1971, 61-79-68, flown by Majors Thomas B. Estes and Dwayne Seavick, flew over 15,000 miles in 10 hours 30 minutes. This flight was awarded the 1971 Mackay Trophy for the Most Meritorious Flight of the Year, and the 1972 Harmon Trophy for Most Outstanding International Achievement in the Art Science of Aeronautics. When the SR-71 was retired in 1990, one Blackbird was flown from its birthplace at United States Air Force Plant 42 in Palmdale, California, to go on exhibit at what is now the Smithsonian Institution's Stephen F. Udvar-Hazy Center in Chantilly, Virginia. On March 6, 1990, Lieutenant Colonel Raymond E. Ed Yielding and Lieutenant Colonel Joseph T. J.T. Vida piloted SR-71 seconds per Newton 61-79-72 on its final senior crown flight and set 4 new speed records in the process. Los Angeles, California, to Washington, D.C., distance 2,299.7 miles, average speed 2,144.8 miles per hour, and an elapsed time of 64 minutes 20 seconds. West Coast to East Coast, distance 2,404 miles, average speed 2,124.5 miles per hour, and an elapsed time of 67 minutes 54 seconds. Kansas City, Missouri, to Washington, D.C., distance 942 miles, average speed 2,176 miles per hour, and an elapsed time of 25 minutes 59 seconds. St. Louis, Missouri, to Cincinnati, Ohio, distance 311.4 miles, average speed 2,189.9 miles per hour, and an elapsed time of 8 minutes 32 seconds. These 4 speed records were accepted by the National Aeronautic Association, the recognized body for aviation records in the United States. Additionally, Air and Space reported that the Air Force clocked the Blackbird at one point in its flight reaching 2,242.48 mile per hour. After the Los Angeles-Washington flight, Senator John Glenn addressed the United States Senate, chastening the Department of Defense for not using the SR-71 to its full potential. Mr. President, the termination of the SR-71 was a grave mistake and could place our nation at a serious disadvantage in the event of a future crisis. Yesterday's historic transcontinental flight was a sad memorial to our short-sighted policy in strategic aerial reconnaissance. Successor. Much speculation existed regarding a replacement for the SR-71, most notably the rumored aircraft codenamed Aurora. This is due to limitations of spy satellites, which are governed by the laws of orbital mechanics. It may take up to 24 hours before a satellite is in proper orbit to photograph a particular target, far longer than a reconnaissance plane. Spy planes can provide the most current intelligence information and collect it when lighting conditions are optimum. The flyover orbit of spy satellites may also be predicted and can allow the enemy to hide assets when they know the satellite is above, a drawback not shared by spy planes. These factors have led many to doubt that the U.S. has abandoned the concept of spy planes to complement reconnaissance satellites. Unmanned aerial vehicles are also used for much aerial reconnaissance in the 21st century. They have the advantage of being able to overfly hostile territory without putting human pilots at risk, as well as being smaller and harder to detect than a man-carrying aircraft. On November 1, 2013, media outlets reported that Skunk Works has been working on an unmanned reconnaissance airplane it has named SR-72, which would fly twice as fast at Mach 6. However, the Air Force is officially pursuing the Northrop Grumman RQ-180 UAV to take up the SR-71 strategic ISR role. Variants: SR-71A was the main production variant. SR-71B was a trainer variant. SR-71C was a hybrid aircraft composed of the rear fuselage of the first YF-12A and the forward fuselage from an Steradian-71 static test unit. The YF-12 had been wrecked in a 1966 landing accident. This Blackbird was seemingly not quite straight and had yaw at supersonic speeds. It was nicknamed the Bastard. Accidents and aircraft disposition: 12 SR-71s were lost and 1 pilot died in accidents during the aircraft's service career. 11 of these accidents happened between 1966 and 1972. Notes: many secondary references use apparently incorrect 64 series aircraft serial numbers, but no primary government documents have been found to support this. After completion of all USAF and NASA SR-71 operations at Edwards AFB, the SR-71 flight simulator was moved in July 2006 to the Frontiers of Flight Museum at Love Field Airport in Dallas, Texas. Operators: United States Air Force, Strategic Air Command, 9th Strategic Reconnaissance Wing, Bill AFB, California. 1st Strategic Reconnaissance Squadron 1966-90, 99th Strategic Reconnaissance Squadron 1966-71, Detachment 1. Kadena AB, Japan 1968-90, Detachment 4. RAF Mildenhall, UK 1976-90, also operated from 4 locations at Griffiths AFB, New York. Elielson AFB, Alaska. Seymour Johnson AFB, North Carolina. Boda, Norway and Diego Garcia. Air Combat Command, Detachment 2, 9th Reconnaissance Wing, Edwards AFB, California, 1995-97, Air Force Flight Test Center, Edwards AFB, CAR. 1129th Special Activities Squadron 1964-68, 1130th Air Technical Training Group 1969-74, 4786th Test Squadron 1965-70 Steradians-71 Flight Test Group 1974-90. National Aeronautics and Space Administration, NASA. Dryden Flight Research Center, Edwards AFB, California, 1992-99. Specifications. Data from ESA-71.org, PACE, General Characteristics, Crew, 2, Payload, 3,500 pounds of sensors, length, 107 feet 5 inches, wingspan, 55 feet 7 in, height, 18 feet 6 in, wing area, 1,800 feet 2, empty weight, 67,500 pounds, loaded weight, 152,000 pounds, max takeoff weight, 172,000 pounds, power plant, TUA, Pratt & Whitney J58-1 continuous bleed after burning turbojets, 34,000 pound forces each, wheel track, 16 AFT-8A. In, wheelbase, 37 AFT-10 in, aspect ratio, 1.7, performance, maximum speed, Mach 3.3 at 80,000 AFT, range, 2,900 mi, ferry range, 3,200 mi, service ceiling, 85,000 feet, rate of climb, 11,820 feet per meter, wing loading, 84 pounds FTA squared, thrust weight, 0.44, see also. Aircraft in fiction SR-71 Blackbird, Linear Aerospike Senior 71 Experiment, Measurement and Signature Intelligence, Related Development, Lockheed A-12, Lockheed YF-12, Lockheed A-21, Aircraft of comparable role, configuration and era, Bristol 188, Cybina SR, Peripheral Vision Horizon Display, an instrument that was originally specifically developed for the SR-71. Related lists, List of military aircraft of the United States, List of Lockheed aircraft, References, Footnotes. Citations. Bibliography. Additional sources. External links, SR-71.org site, the online Blackbird Museum, habu.org, Where Are They Now? Map of every Blackbird location, blackbirds.net, SR-71 Blackbird photographs and videos at NASA's Dryden Flight Research Center's website, SR-71 Flight Manual, summary of SR-71 serial numbers. The Senior 71 pilot full pressure suit, surviving the breakup of SR-71 at Mach 3.18, Peter Law's detailed technical presentations on SR-71 thermal and propulsion design features.